You and a friend are tasked with measuring the length of a river for part of a class project, but you both choose different measuring units based on how much time you want to spend on it. You choose a 20-kilometer measuring unit and find the length of the river to be 600 kilometers. However, your friend uses a 60-kilometer measuring unit and finds the length of the river to be 400 kilometers. But how could you and your friend come up with such vastly different measurements of the same thing? Well, you have both fallen victim to something called the Coastline Paradox. What is the Coastline Paradox? The Coastline Paradox is a counterintuitive observation that the coastline of a landmass does not have one finite length, and it results from the properties of fractals that apply to it. It tells us that the smaller the ruler used, the longer the length of what is being measured will be. As is seen in this animation, as the length of the measuring units increase, shapes become more ill-defined and their length decreases. This is because the more smaller measuring units being used, the more imperfections in the landmass are being measured. And as smaller and smaller measuring units are being used, the more imperfections are being measured. Theoretically, you can use infinitely small units, measuring down to the imperfections in atoms, essentially creating an infinite length of whatever is being measured. For example, consider this to be part of the rocky coastline of northern Scotland. And as we zoom in on a rock within that coastline, we can see the imperfections in its edge. It is not yet easy enough to measure, so we zoom in even further. We can still see imperfections there as well. So, again, we magnify to see the atom that makes up the molecule, that makes up the rock, that makes up the coast. However, we can still see imperfections here. What can be deduced from this illustration is that at every level of magnification, there are still imperfections that can be measured. Who discovered the Coastline Paradox? In 1951, Lewis Fry Richardson, an English mathematician, discovered what would later be known as the Coastline Paradox. While researching the effect border length had on war, Richardson discovered that Spain had measured their border along Portugal as 1,214 kilometers. However, Portugal had measured the same border as 987 kilometers. The large difference in measurements caught his eye, and he began experimenting to find out how the two countries could have such vastly different measurements of the same thing. He discovered that, depending upon the size of the ruler used, the measurement would either increase or decrease in length. A similar concept lies within the curve of a circle. The more line segments used to measure the circumference, the longer the length will be. After testing, Richardson has concluded that Spain and Portugal had simply used different measuring units to measure their border, thus creating the inconsistency. But what are fractals, and how do they relate to the Coastline Paradox? Benoit Mandelbrot, a Polish scientist, discovered a new branch of mathematics that he called fractal geometry. Fractals can be used to describe non-measurable forms in nature, and they rely on the assumption that space can be subdivided indefinitely, and is purely a theory. Examples of fractals in real life are things such as river networks, mountain ranges, lightning bolts, trees, snowflakes, crystals, DNA, and of course, coastlines. An important property of fractals is self-similarity. This refers to the patterns that will appear at any level of magnification. A popular example of a fractal is the Sierpinski triangle. The Sierpinski triangle is an equilateral triangle, infinitely subdivided into smaller equilateral triangles while following a specific pattern. In the Sierpinski triangle, the same pattern can be observed at any level of magnification. Another popular example of a fractal is something called the Koch snowflake, which starts as an equilateral triangle and then replaces the middle third of every segment with a pair of lines that forms an equilateral bump. This can be applied to the coastline paradox in a very obvious way. Let's assume that an edge represents the imprecise measurement of a portion of the coastline. Well, we can zoom in further to place the bump to represent a protruding landmass. Again, there are imperfections within that protruding landmass, so we place more triangles to represent those. We continue placing triangles until infinity, so that the same pattern can be observed at any level of magnification. As we can see in this animation, within the Koch snowflake, the same pattern occurs at any level of magnification, due to the pattern of triangles that are placed. In the same way as the Koch snowflake, coastlines consist of bays with just of land protruding from them. So, in the hypothetical situation that the coastline paradox corresponds with these principles, coastlines cannot be measured. How does the coastline paradox affect me? Waterfront home builders have needed to use consistent unit of measurement to block off sections of land for construction. If they do not, then properties might overlap, causing construction problems. And, like how Richardson found, countries need to use consistent unit of measurement to maintain a scaled representation of the coastlines and borders. This has been the Coastline Paradox and Fractals by John Fennell. Thanks for watching.